And let's move now to the second presentation that is going to be given by Paul Axtell. Paul, the floor is yours.
Gerald. Okay, here we go. Well, I'll echo what Van said. Thanks everybody for attending. I appreciate you giving your time to this. Certainly my pleasure to be invited to participate. Van, great job. Also, excellent segue. The project that I'm going to discuss today also involved use of an oscillator. Also had a very wide range of soil particle sizes that we had to deal with. And so a great segue from your project into mine. Today, to illustrate the value of additional testing following the It's Money theme, I'm going to talk about a bridge project we were involved with. It's the Sellwood Bridge. We did some additional foundation engineering to optimize really both design and construction. Again, my name is Paul Axtell. I'm with Dan Brown & Associates. Another one of our guys that was involved was Nathan Glinsky. He did a lot of time in the field, as you'll get to know when we walk through this presentation. I'd also like to recognize Mike Lopez, who contributed. He's a structural engineer, senior bridge engineer for Jacobs, and formerly of T.Y. Lin. This presentation, quick outline, I'll give you some background on the location of the project and a little overview, including some historical facts. I can't do any presentation like this without having some basic understanding of the local geology. I'll give you the background on the basis for the value engineering design. In fact, that's where Dan Brown & Associates got involved in the project. Most important to the performance of any drilled foundation is the construction. And so in my experience, the performance of drilled foundations, particularly large diameter drilled foundations, it's mostly governed by the way the shafts were constructed. So very important in my judgment to thoroughly understand construction methodology as it relates to performance of foundations. Design criteria, that's what we came up with as part of our VE design, and then we'll tie it up with a bow in a summary. The site location is just south of Portland, Oregon. It's called the Sellwood Bridge. It crosses the Willamette River. We've done several bridges in the area. It's a pretty, you know, as far as span lengths go, not a major structure, but it's certainly a iconic structure that the city was and the county was interested in having a signature bridge. Some facts about the new project: it's going to be an steel deck arch structure. It's going to be widened 15 feet relative to the existing structure. That includes two 12-foot travel lanes, two 12-foot shared use sidewalks. And like I said, it's in Portland, so there will be bike lanes, which as a bike rider, I love. The foundations for the new bridge are roughly 10-foot diameter. They're 3 meter diameter shafts. Again, going back to the use of an oscillator and typical metric units. Original design had the foundations tipped in basalt bedrock, and our involvement came after award. We were not involved in the original design or scoping of the project, but rather we got involved when the contractor you know, wanted to make some changes, and we got involved through a VE project or VE approach. A couple other interesting facts that aren't shown on the slide: the new bridge is placed on the existing or the original alignment. So kind of a neat part of this job. The existing structure, which was, you know, 80, 85, 90 years old, was actually moved laterally onto a temporary pile bent system. And that existing structure, although put onto a slightly new alignment, did have to remain in service during the entire construction. So take a really fragile old bridge, move it laterally 20 or 30 feet, and keep it open during major bridge construction was no small feat. I love these old type photos. The original structure was opened in 1925. As you can see in the photo there, a 4-span continuous truss design. You know, things we deal with today, they were dealing with in the 20s. How many of us have had a project that was underwent some political turmoil that resulted in a slashed or reduced budget? And so interestingly enough, following that turmoil, the approach girders were reused from the Burnside Bridge, which is basically located in downtown Portland. So just a few miles downstream of this existing structure. You may ask, why is the bridge being replaced? Well, it's in the National Bridge Inventory. It's got a sufficiency rating of 2 out of 100. I don't know all the details of that rating system, but a 2 out of 100 seems pretty low to me. They've had to deal with cracking and sagging in several iterations throughout its recent life. Reinforcement and bracing were required in many locations. Local geology, like I said, it's in the Willamette River Valley. That valley is formed by the Coast Range and the Cascade Mountains. It's characterized by periods of uprising. There's lava flow. Like I said, basalt bedrock exists. Coastal collisions, glacial floods, and you can imagine from such a chaotic geologic environment that the material and the top surface of rock and whatnot are highly variable, and certainly that is a difficult hurdle to jump in design and construction. More specific to the site and from the top down, the 4 strata, the primary strata that were present, starting at the mud line, you have alluvial sands. These are very low shear strength, very weak, recent deposits. We're not going to spend much time on them, basically because through the design of the permanent works, this material is really neglected in the design. If the river put it there, the river can take it away. It's sort of the easy way to look at it. Beneath the alluvial sands is the catastrophic flood deposit. We refer to it as a CFD. That overlies the sort of notorious Troutdale Formation. If you've worked in Portland, you're familiar with the Troutdale, I'm sure. And then all of that sitting on top of basalt of the Waverly Heights. Subsurface profile, more or less at bent 4. You can sort of see the variability. Those polka dots at the bottom of each of these stick logs represents the basalt bedrock. And so, there's 5 borings shown here, but they're not really exactly at bent 4, and they're certainly not at each drilled shaft location. But the original design was developed with requiring a 20-foot long, basically arbitrarily requiring a 20-foot long rock socket into this basalt bedrock. And it appears the original design took the sort of the worst case or the lowest case bedrock, and that's where their 20-foot socket requirement started. So in some of these borings, it shows a 20-foot socket. Well, if you hit rock in some of the other borings, it's more like a 50-foot long rock socket, okay? And again, we're talking 10-foot diameter shafts over water working from a temporary trestle. So that's no small undertaking. So, I understand the design perspective of sort of covering yourself with the worst case scenario, but that's only conservative for design. In fact, it's very risky for construction, and really that's where the real money is. Okay, look at the CFD deposit. As Van was saying, we got particle size that range from sand to boulders, and when I'm thinking boulders, I'm thinking 1 foot, minimum 1 foot dimension of the particle, and cobbles in between. So this is a picture of the CFD as it's being excavated with the grab. Certainly you can see and you can appreciate how difficult a material this would be to sample and characterize. SPT would obviously be basically refusal blow counts based on particle size, but may not be a very good indicator of the in situ density. You can imagine how difficult it'd be to push CPT. So really you've got to appreciate how difficult it is to drill and sample and characterize this material. On the other hand, if you imagine a drilled shaft with concrete cast against this material, it doesn't take much imagination to come up with a really decent nominal unit side resistance if we've got good concrete bond to this material. But also you can imagine some difficulties with respect to drilled shaft construction. Troutdale Formation, pretty similar to the CFD, poorly graded gravel with silt and sand, probably on generally a little bit smaller particle size, but still sub-rounded. It's a very weakly cemented conglomerate, and if you did SPT testing, you see again very dense refusal blow count type material. We have done lots of bidirectional static load testing in this valley and bridges just upstream of this particular bridge, and those bidirectional tests led us to believe that if shafts are constructed properly, this Troutdale Formation can provide excellent load carrying capacity. So what appeared to be very little contribution was given to it in the original design. This material, it does exist out there. It does provide great resistance to both axial and lateral demands. And in our judgment and that of the contractor, we thought through some additional testing and observation, we ought to count on this material to optimize the design. A few other photos coming up here about what the Troutdale looks like. When it comes down to additional testing, we had our engineer who was intimately familiar with the design, knew what we needed out of each shaft, and was familiar with the materials. We've got that engineer down in the spoils barge looking at each load that comes out of the grab. And so when you find a nice piece of cemented Troutdale like this, it's very easy to recognize that you're no longer in the CFD. So that transition is very important. And so each yard of material that comes out in the grab, our engineers down there looking at to try and verify the material that we're seeing, that we're relying on. And just a few more pieces of cemented Troutdale. But as we're excavating the shaft, remember we're doing it with a big grab. And so when you come out with several yards come out in each bite, and it goes over to the spoils barge and it dumps in the spoils barge, a lot of that weak cementation gets destroyed. And so sometimes the color variation is so subtle between the CFD and the Troutdale, it's very difficult to know that you're in the Troutdale. And so, when the grab destroys the cementation, you really got to have a qualified engineer looking through it to make sure you are in the right material for design. So again, additional testing, not traditional testing in the sense that Van just went over. We're not trying to improve upon resistance factor. We're not trying to improve upon the resistance values. We're just trying to take a hands-on approach to address the variability by the observational method. Beneath the Troutdale, the basalt of the Waverly Heights, it ranges in hardness from R2 to R5. If you're not in the Pacific Northwest, maybe that rating system doesn't mean much to you, but I've got a table here in a few slides where we'll go over it. Basically, the higher the number, R5 is very hard rock, and so R0 is very soft rock, so everywhere in between. Average uniaxial strength of this rock was on the order of 12 KSI, so nice hard rock. No indications in the borings that there would be any solution cavities or voids or anything that would make us reluctant to rely on base resistance in this rock. That base resistance is there whether you're on the top of rock 20 feet or 50 feet into that rock. So as we all know, the area of a drilled shaft is a function of the diameter squared. So as we get to these big shafts, 10-foot diameter shafts, the contribution of base resistance is through the roof. It's a function squared. So if we can get them built right, and by that I mean cleaned and inspected and concrete placed properly, there is tremendous base resistance that can be realized in these large diameter shafts on rock of this quality. Certainly we recognize that from the borings and the geologic environment, we knew the top of bedrock is highly variable. And that's another reason why the additional testing by having an engineer out on site paid dividends. And I'll just reiterate, the conservative design assumptions that were made originally, that's only conservative for design. For the overall project, it's actually unconservative. One more photo of the basalt after being busted open with the geologic pick, really, really high quality rock. All right, the basis of the value engineering design. So here after the contract's awarded, Malcolm Drilling is getting ready to go out there and put in drilled shafts. We got on board to help develop a value engineering proposal. As I noted earlier, the original design assumed the worst possible conditions based on the borings. And there were limited boring information. I know that cross-section I presented had five holes, 5 borings, but they weren't all where they needed to be. Also identified how difficult the material is to sample, and we certainly recognize the difficulty when dealing with highly variable conditions. The end product for the original design was a minimum 20-foot rock socket into the basalt on all these shafts. That posed a very serious risk to constructability. At the deepest point, some of these shafts are on the order of 220 feet deep, being constructed using an oscillator on top of a temporary work trestle. So there's an old saying in drilled shaft construction, every foot deeper you go is 1 foot closer to hell. And so it's best to be avoided if you can. Again, a little bit off tangent, our VE studies that we have participated in over the last couple of decades, typically we find there's got to be something more to it than just money. I mean, we all know how important money is with respect to construction, but the reality of it is for the contractors to want to take on the design burden, to want to take liability for the design over, there's got to be more incentive than just material savings, typically. In this case, mitigating the risk to constructability was how we got our foot in the door with this VE. We can continuing the basic VE was developed and accepted, and we were looking to reduce the length of the rock socket and mitigate construction risks. The additional testing that comes through this that's pertinent to this webinar is the emphasis on quality assurance by an engineer who is intimately familiar with the design requirements and the material. Because to address the variability, it also provided design flexibility in real time. And so that wasn't just at a whim. We knew the variability that we might expect, and so we developed, before we went out there, we did our homework and we developed a certain decision matrix and flow chart. If we encounter this much of this material, it's worth X, Y, Z, and so on. Those decisions were made real time in the field with an engineer. Provided great flexibility to accommodate the variations. So our role after VE design was submitted and accepted, we were to be on site at all times during excavation, classify the materials, and come up with those target tip elevations on site. Again, in real time, but not on a whim. I mean, we had done our homework. Also, we were there to verify bearing conditions. So we're very big proponents on relying on both side and base resistance. Numerous load tests have demonstrated that both can be relied upon at compatible strains. But for base resistance, it's highly dependent on the construction. So is side resistance to some extent, but the base resistance, particularly on large shafts where the magnitude is so ginormous, it's very important to make sure we have a clean base and it's verified. So we did that with airlift and in the mini SID we'll get to a little bit later. And certainly schedule is king, as Van alluded to in his presentation. So we were working to help Malcolm get the drill shafts installed as quick as we could. Installation method, we were using full length segmental casing with an oscillator. Most of it was temporary, but the first starter piece was a permanent case. So as we oscillated back out, we left that last piece of casing in the ground. That was effectively our form from the mud line up through the water when we placed the concrete. Polymer slurry was used, although it wasn't necessary for hole support. That's what the temporary casing was for. And the rock socket had no problem staying open on its own. But the polymer can help when it comes to getting the segmental casing back out of the ground. Working right next to a existing structure, so uncased wasn't an option. And in this type of material, the CFD, highly unlikely a slurry supported hole would have worked. I said we used an oscillator. You've seen the soil and the rock, and so the rock was excavated using a chisel, basically bludgeoned it to death and going with the grab. A few pictures, the oscillator setup. You can see the temporary casing at the top. It's a bolted connection, very expensive casing. The oscillator is what's surrounding that casing. It's connected via yoke to the crane. That same crane is used to do the digging as well. In this photo, the yellow line there, that's the airlifting or vacuum. That's used to clean the base of the shaft. You get rid of the cuttings and also all the solids that precipitate out of the slurry column. So you clean all that out of there with the airlift. The white hose going into is just the replenish hose to ensure we maintain a positive head. Again, it's another look at the yoke that connects the oscillator to the crane. The grab, you can see the grab, the same crane that the oscillator is attached to is operating this giant spherical grab. It goes down, takes a bite, comes out, swings over and dumps into the spoils barge. And then our field engineer gets his hip boots on and mucks around in there looking to verify materials that are being encountered. The chisel I talked about, I'm going from memory here, but this is, I believe, a 40,000 pound hunk of steel. Of course, it's a little bit less than that when it's in the slurry and buoyant, but this is a giant piece of equipment. All these pieces of equipment are giant. Forces are tough to even comprehend the magnitude of force that can be delivered by these machines. But in the upper photo on the right, even the chisel, even that giant chunk of steel is prone to damage. When you're dropping it on screaming hard rock, it beats the rock up, but it takes a beating too. The picture on the lower right shows a piece of permanent casing at the bottom that got fouled up. And as we dropped the chisel, it actually busted that 2.5-inch wall steel. So tremendous forces we're dealing with. How does that relate to constructability? Well, you can imagine as we drop this chisel on screaming hard rock, all the vibrations that come about. And if we have vibrations, there's more chance for this granular material to cave in against the casing, and you risk losing the casing. And this is very expensive casing that no one wants to leave behind. So that's sort of an insight into the construction risk that we were hoping to mitigate. Moving into the actual design, at Bent 4, that's located towards the western shoreline. It's a 1x4 group of drilled shafts. Our VE design required at least 12.5-foot rock sockets, so quite a bit different than 20 or 50. Same thing with the Vans project. In typical of bridges over water that are with the foundation bearing in firm soils or rocks, really that 12.5 feet socket length was plenty good to resist demand to the strength limit state and extreme event loading. And that 12.5 foot was only necessary for lateral considerations, so seismic and vessel collision. The flow chart or the design matrix, depending on where top of bedrock was encountered, either had a 15-foot long rock socket in the basalt of grade R2 or better. But if we hit rock a little bit deeper, we could reduce that down to 12.5 feet, okay? Because that extra 20 feet of embedment in the Troutdale, that provides axial and lateral resistance too. It ought to be counted on for something. And then in all cases, we had a minimum tip as well. I alluded to the fact that we're relying on base resistance. And so to do that, like I said earlier, we airlifted to vacuum clean the base. And then we monitored verified the cleanliness with each shaft with the mini SID, basically a camera that's capable of looking straight down at the base of the shaft through slurry or water or anything else. The cleanliness criteria was pretty typical, 1/2 inch over 50% or less, and nothing more than 2 inches. Of course, this is done prior to the cage going in, and putting in the cage and the concrete on a shaft this size over water is no small deal itself. Moving on to Bent 5, located closer to the eastern shoreline, same thing, a 1x4 group of shafts. Bedrock here is quite a bit deeper. Again, the VE design was specified a 10-foot rock socket of either Troutdale or basalt. They both satisfied what was needed. Tip elevation again was a minimum was provided, and DBA engineer was out there to classify the spoils and make sure that we were bearing in the right material. Again, mini SID and DBA approval prior to acceptance of the shaft prior to concreting. A couple photos of Bent 5. This is the first starter piece of casing. It's going to remain permanent. During construction, it makes its way all the way down to rock. You may not be able to make it out, but there are rock teeth at the bottom of that piece of casing. Then as we're placing concrete and we're getting the temporary segmental casing back out of the ground, this piece of steel stays in. And like I said, that's the permanent form coming out through the water. The photo on the right shows the cage placement. Again, for a very deep shaft like this at Bent 5, you've got to splice the cage. You've got a really small working area on this trestle bridge. So it's quite an ordeal, a very nicely orchestrated dance to get this all to work on such a small footprint. Another shot at Bent 5, and I like this photo because it shows, one, the existing structure that's on temporary piling, and how close we are to that structure. And two, this whole setup, oscillator and crane are working on a temporary trestle. As this oscillator is working to get this casing down and back out of the ground, tremendous lateral forces are being applied through that yoke to the crane, and then the crane is transferring that force to the trestle. So if the trestle is not designed properly for these giant lateral loads that are placed way up high in the ground, way up high in the air basically above the point of fixity, very large deflections of that trestle occur, which there's direct safety implications as well as braking. but they also can play havoc on the alignment of the casing and further increase the risk of getting your casing stuck. So if you're designing an oscillator job or you're working on an oscillator job, make sure you think about the deflection of the bridge, of the trestle. Bent 6, this was actually an anchor pier. It's located on the eastern shore. It's a 2x3 group of shafts. We required a minimum 7-foot rock socket and up to 15 feet, depending on where we encountered rock. Obviously, this configuration provides frame action in the longitudinal direction of the bridge. The design criteria at Bent 6, where we had Troutdale or weathered rock, we needed 7-foot length of Troutdale of grade 1 or better, or bedrock of grade R1 or better, plus an additional 12 feet of length in the basalt. If we didn't have Troutdale or weathered rock, then we needed a 15-foot rock socket. In all cases, again, we had a minimum tip. So here's a picture of Bent 6. Interesting, you can see the original alignment in the bridge that's been shifted over to the left. And to the right of the photo, next to that crane boom, you can see the new bridge piers that are going to be coming over right between two pretty high-priced condominiums. And so real estate, of course, was premium. The rock hardness scale that I alluded to, as you can see, R0 is less than 100 PSI, and R5 is very hard or greater than 16,000 PSI. Obviously, when we're out in the field, we're not breaking uniaxial core samples, so we don't directly know or measure the uniaxial strength, but we have tools in our toolbox to identify the material in the field using fingernails, pocket knives, and a geologic pick. And so our engineers spend a lot of time scraping spoils and busting them with a geologic pick to estimate the grade of the rock. So in summary, the VE design was successful in mitigating the construction risks, reduced the rock socket lengths, and of course the dollars associated with material savings on every shaft that we were involved with. We estimated the savings about a little over 220 foot of rock socket. So that's 220 foot of 10-foot diameter rock socket and 12,000 PSI rock. The additional testing part of it came from the need for a site inspector that's a qualified engineer, familiar with the design, familiar with the materials. It provided flexibility in a way to address the variability in the subsurface conditions. But again, it relied heavily on that individual being highly qualified. It's money, we're getting back to that theme. About $1 million in direct cost savings from that 224 foot of rock socket reduction. And like Van said, that's not including the benefit of the reduced construction risk. It's tough to quantify. It's kind of a subjective scale for what is the dollar value of reduced construction risk, but it is real. And so that $1 million savings, $1 million plus savings, was realized for about 200 grand to have an on-site engineer out there, including travel expenses. So at a minimum, a delta of about 800 grand, certainly a big enough number to concern yourself with. That's all I've got. I'd like to thank Malcolm. They did a great job. T.Y. Lynn, they were the bridge designer, Jacobs and the Multnomah County, who was the owner of the project. And also I'd like to thank the Sladen Soont JV. So with that, I will, if we got time, take questions. If not, Gerald, back to you.
Thanks, Paul, for, again, a very interesting presentation. That certainly shows the It's Money theme. One question.